Okay, this is the second video from chapter 12. This one deals with the concept of angular momentum. Now, angular momentum is a tremendously useful idea, and also, if you do it in fully three-dimensional problems, incredibly difficult. But you will not have to do fully three-dimensional problems. Everything will be basically two-dimensional, which makes it pretty easy. Now, our definition of angular momentum is going to be r cross p. The idea is that if you've got some particle of mass m moving with speed v, you know that it has linear momentum p equals mv. That's old hat. Now, if we have the origin here, or pivot point, and you can pick that to be almost wherever you want it to be, you can draw the radius vector r from the origin to the location of that point mass. So it's got a velocity vector v and a position vector r. And that means we can also define an angle between r and v, theta, like that. And we can say that the angular momentum L is equal to r cross p. The magnitude of L is r times m times v times the sine of theta. And the direction of L in this case, if we point the index finger in the direction of r, the other three fingers in the direction of v, you find out that the angular momentum as a vector points into the board. Now, the other way of thinking about it is if you draw the particle's path, and then you look at the closest it comes to the origin, you can define another r perpendicular, which is the closest distance. And you can say, in this case, that the angular momentum is just r perpendicular times p, because you can show that r perpendicular equals r sine theta. It takes a couple steps of geometry to do that, but it's not all that hard to figure out. Notice that the actual value of the angular momentum does depend on where you pick your origin, which is interesting. So if you just ask, what is the angular momentum of this particle, that question is meaningless. It needs to be, what is the angular momentum about such and such point? That would be what you have to ask, because it does matter about which point you calculate it. And then if you've got multiple particles and you need to find the total angular momentum, you just find the angular momentum of each of them individually and add those up, keeping in mind the difference between angular momentum into the page and out of the page. Now, at the beginning of the video, when I said you wouldn't have to do any fully 3D problems, what that means is you'll deal with 2D problems so that all of your L's either point into the page or out of the page. And come back, please, onto the next slide. Now, looking at this again, if we have a particle moving in a straight line, so particle of mass m moving with speed v in a straight line, there's its path. Now, if we want to find come back here, thank you. If we want to find the angular momentum about that point, so that's r. So I'll do it about origin 1. I'll label that 1. The angular momentum is equal to mv, and I'll call that r perpendicular 1. Now if I pick origin 2 here, the angular momentum about origin 2 is mv times r perpendicular 2. So that's r2, and that's r perpendicular 2. Notice that regardless of which point you choose, the angular momentum of the particle will stay constant as the particle moves. So, regardless of which point, L is constant as the particle moves. And that means that we can say that angular momentum is conserved. Now that's all we're going to say about conservation of angular momentum in this video, but you'll see in the next video we'll talk a lot more about conservation of angular momentum, and we'll look at under exactly what circumstances angular momentum is conserved. For now, we're just going to calculate it. But if you remember back to linear momentum, you'll remember that the angular momentum of a particle is p equals mv. So if you have a solid object that is rotating, we'd expect that its angular momentum would be the equivalent of mass times the equivalent of speed, which is I omega, moment of inertia times the angular speed. And in this case, the vector L will be defined, because remember omega and L are vectors. You curl your right hand, or the fingers of your right hand, in the direction of the rotation, and that will make your thumb point in the direction of L. And for some reason, your textbook and most others use capital L when referring to the angular momentum of a solid object, and lowercase l when referring to the angular momentum of a point mass. I don't know why, it's just what they do. And now, if you recall Newton's second law for rotation, what we said was the net torque equals I alpha, which is I times d omega dt. Now, if we say that I is not changing, which is reasonable, we can say that the net torque is therefore equal to the derivative of I omega, which is the rate of change of the angular momentum. And you'll notice that this is entirely analogous to the linear equation, net force equals dp dt. Once again, all the ideas you have from linear physics works in the rotational case as well. And last of all, we'll do an example. We've got a sanding disk. You're given the rotational inertia. Notice it's quite small. It's attached to an electric drill, and you're given the torque delivered by the motor. And we want to find the angular momentum and angular speed of the disk 33 milliseconds, that's about 1/30th of a second, after the drill is turned on. So for this, we'll use Newton's second law, which says the change in L equals the torque times the time, which is torque is 16 Newton meters, time is 0.033 seconds, and that's 0.528. The units are Newton meters per second. And so that is the answer to part A. The answer to part B, we want to find the angular speed. Well, for this we use L equals I omega, or omega equals L over I, plugging numbers in. And I is 1.2 times 10 to the minus 3 kilogram meters squared. And it works out to be 440. And this is fairly complicated units. Remember, a Newton is a kilogram meter per second squared times meters per second, all divided by kilogram meters squared. second squared. And that cancels out. Oh wait, hold on, it's not Newton meters per second. So this is why I like normal lecture better. It's Newton meters seconds is the unit of angular momentum. And so that cancels out, and you're left with 1/seconds for the units. And we know that that is really radians per second because the radian is kind of a fake unit. And that was a very easy problem, but it does give you a sense for how you use this. And really, you're not going to see very many really difficult problems that deal with angular momentum until you get conservation of angular momentum, which is what we'll look at the next video. So for now, it's easy. And what I'd like you to do for tomorrow are questions 5 and 6. That's what I'll be checking in class.